So hello. So we are now entering the last part of the course, and we will talk about modeling for epidemiology. And the kind of models that we will develop are kind of what people in epidemiology say are ecological models, which is something which has a different meaning in epidemiology, because epidemiology, I mean, has many aspects, but looking at the populational level, as we have done with ecology, is called by epidemiologists an ecological view of epidemiology. So we will start this with a historical background, and I spent some time talking about some of the diseases that were very important in the history of humankind. And we will develop the simplest model that many of you have probably heard. Due to COVID, everybody has heard about some kind of model and so on. But we will build this, and we will discuss concepts like the basic reproductive number, or the herd immunity threshold, or effective reproduction number, these kinds of things. Maybe not today, but I mean maybe on Friday. So, and then once you learn the SIR model, how it was built, you will see it will be easy to build other models. And I will come to this when we talk about SIR. Okay. So, about references, if you are interested in the subject with a mathematical touch, this is kind of basic textbook. It's called Modeling Infectious Disease in Human and Animals. Okay? There are others, there are many others, classical books like from Anderson and May, and more mathematical ones. But I have also a suggestion to those that are not so mathematically minded, but maybe would like to know a little bit about the history of how diseases have been interacting with the society. There's a very nice book which is called Epidemics and Society. I don't have it here because I have it only on my as a I would say Kindle thing online. Yeah. So, but take a look. This will be very, very interesting readings. So, plague. So, this is maybe the first written description about a disease, of an epidemic, and this is called the Plague of Athens, which is not to be, this is not bubonic plague. It's just the name plague is used in a very general way. So this was in the time of the Peloponnesus War, and say the father of history, Thucydides, described this as having heats in the head, hard cough, discharges, and 1/3 of the population died. 1/3. So, including Pericles. So, people don't know for sure. It is considered the most popular is typhus, which is the etiological agent is a bacterium transmitted by lice. And it came somehow from Africa through the Mediterranean, and from Egypt probably. So then you have this quotation here, if you want, about how this disease acted. So this is first mention of an epidemic in Britain history. And there's still discussions about this. So what was the disease? And this is it's difficult because you have only this kind of description, which is not exactly a medical description. It's just like a historian. But people tried to find evidence, paleological evidence from graves, which can be connected to this time. So that's where the hypothesis of typhus emerged, but still matter of some discussions. So then, actually, epidemics of plague. So plague has been one of the major diseases that has shaped human societies. Plague is transmitted by a bacterium, and it can be that's called pneumonic, bubonic, or septicemic. All of them lead in high proportions to death. And antibiotics are efficient, and that's can be, but you have to be treated quickly. Obviously, when plague first appeared in, at least in history. So there were 3 big pandemics, and there was this one called the plague of Justinian, during the reign of Justinian, which was in Constantinople. 25%, I mean, started in Constantinople, killed 25% of the Mediterranean population. So it's estimative. Obviously, there are no records. Okay? So, and curiously, it did not propagate into into Europe and through the inner part. Okay? That's probably because this is Middle Ages. Okay? It's high Middle Ages. It's like year 800. Very few roots. Not so many real towns or cities. It's feudalism and so on. And then probably it did not go inside. Okay? But the Black Death, which is in the 14th century, actually swept around the whole Europe, and it entered from Sicily, and the bubonic plague. I mean, there are 2 big waves. This is one. And the other one is in the 17th century, and then it disappears. Disappears from Europe, of more or less unknown reasons. That probably has to do with changes in the way that people lived in cities. And then there's this big 3rd pandemic, which is the end of the middle and the end of the 19th century, and mainly in China and India, and also in Indochina, in Vietnam, and so on. It was very important. It still exists, and it's usually connected to arid regions, like the south of United States. And also there's plague, where in the United States it's usually not a very serious problem because the wide existence and availability of antibiotics. Because it's easy treatable, right? It's a bacteria. And which is not the case necessarily, for instance, where another region where you have plague is Kazakhstan. It's also a big desertic region and so on, and then there are some deaths occurring in some towns, remote towns of Kazakhstan. I think I have here plague for, so that was plague in Brazil, so there was, I mean, not so many, but in rural areas, northeastern and Minas Gerais, and this is number of cases, but over this period it is only 6 persons died, and I don't think there has been other cases after that. So, very good. So, let me see get back. Let me mention here another thing here is plague has played a very important role in the discussion of what are the diseases. Okay? So when we talk about diseases today, we talk about it's virus, that's a bacteria, or whatever. It's a protozoa or whatever. But infectious diseases have existed for so long, but we only know that they are transmitted by microorganisms since the middle of the 19th century. So it's not even 200 years. Okay? So before that, when we are talking about the plague and the Black Death and so on, plague had always been one disease of very difficult to understand, and why? So, plague is transmitted by a flea that bites you, but the flea has before bitten a rat, which also, rats also die from plague. Yeah? So there's an epidemic in the rats, and then usually a lot of the rats die before having the epidemic. That was an early warning signal that rats started to die in large proportions, and then you had the epidemic in the human society. At that time, not at that time, but at say 17th, 18th century, when you have the emergence of, say, scientific medicine more clearly, there was this discussion of what are the diseases and how are they transmitted. So one thing is there could be contagion. Okay? So contagion was essentially discussed in terms of sexually transmitted diseases because people touch each other. But if they don't interact physically, it was kind of, okay, how is it that if I'm here, I'm sick here, somebody else gets sick, but the house next door or something, if they had not been very close. So then there were lots of theories about diseases being connected to the quality of air or having some substance in the air, and that this somehow was the origin of the diseases, okay? Which was actually and plague played an important role, because plague is like I die of plague here and somebody else 1 kilometer from here gets plague from me. So, come on, this cannot be contagion. In principle, people thought about this. Nobody knew that infectious diseases are due to microbes, which would be seen as completely crazy before the 19th century, in the sense that I'm saying that there are little living beings that we cannot see and that go inside us and make us sick. This seemed at a certain time as fantasy. Right? So this would have been fantasy in the 18th century. So there was no clear way of saying, okay, what is it? It's only with the work which starts with Louis Pasteur, which is 1857-58, which he starts when he formulates that the idea that diseases are due to microbes. He has actually worked first with diseases of wine and beer, and well, he found out that fermentation is due to yeast, which is a living being, and then he went on to study diseases of silkworms. And so on. So he formulated that idea, but he could not find exactly. Okay, then he went on for an actual human disease, which is rabies. Rabies, and he was able to formulate a vaccine, but empirically for rabies. Why? Because he could not find the microbes. Because it's a virus, and you need, in order to see a virus, you need an electron microscope. So he could not see. So he just said, well, it's there. I don't see it because maybe it's so small, which is actually true. Okay? But the idea that you could use attenuation and was developed with a disease it's called chicken cholera. So it's called like cholera and so on. That first developed with this. So he said, let's try with rabies. Okay? And well, turned out it worked, and he saved many lives. Okay, so was saying he actually, there was a problem today that would be anti-ethical completely, because first he was not a physician, was a scientist, so he could not inoculate anybody. He cannot treat any person. Right? But when he went on anyhow, okay? And then much later, like in the end of the 20th century, it's discovered you have the books, the notebooks, laboratory notebooks, which has been held secretly by his family, and only back in 1980 something, they were donated to the Library of France, National Library, and then they were studied, and actually he had tried with a person before, and that didn't work. The person died. Okay? I mean, anyhow, the person would probably die anyhow, because this was a person that had been bitten by dogs, and so anyhow, that's how the things worked at that time. So, but this is curious because he actually could not find the thing, and the first person that actually found the microbes, which were bacteria, was Robert Koch in Germany, more or less 1800, I think 70 something. So he found the etiological agent of cholera and of tuberculosis, which are bacteria, therefore it's seeable. You can see this under the microscope. So, and then, due to the work of well, at a certain point in the, I think 1870s or 80s, there's in France this establishment of the Institut Pasteur, which was very important and had branches all over French colonies. Right? So they studied things in many places. So they start with the tropical diseases and so on. It's with Pasteur. And so they had missions. And it is a person which was scientist from the Institut Pasteur, was called Alexander Yersin, which discovered the etiological agent of plague, of bubonic plague. This work was done in what is today Vietnam, that's the French Indochina, and was able to discover this. But then you say, okay, that's nice, but knowing only the agent is not enough. We have to know how it's transmitted, okay? Which can be, sometimes it's non-obvious, as it was in plague. Totally non-obvious. And well, Koch actually was able to see that cholera had to do something with water, which has been empirically already studied by a guy called John Snow in London, which the famous story about there was cholera in London, but he went on and looked where are the cases, in which houses, and they were clustered in a certain region, and all of them got water from a certain pump, right? And then he identified this as the pump. So somehow this is connected, and well, it actually turned out that this was an empirical observation, because nobody knew that anything about bacteria, nothing. I mean, just to see that it has to do with if you treat the water, you don't have cholera. Okay? And this has been a matter of, at that time, before the discovery of Koch, that had been a matter of very heated debate, okay? Because there were the negationists of the time, and there's a story about that things like, for instance, happened in Germany, in the city of Hamburg, and there was a nearby city, which now is part of Hamburg, which is called Altona, and Altona had people that the public health services that believed in John Snow, and they treated water. And then you have an epidemic in the region of Hamburg, and Hamburg has a lot of cases and Altona has none. So that was empirical knowledge. Yeah? So then okay, so when Koch discovers, then you start to understand that there's a bacterium which goes through the stool to water. So there's this oral-fecal transmission. Right? So once you know this, then you can have public health measures. So it's not only knowing the agent, right? You have to know how it's transmitted. And then obviously you say sanitation, and you get no cholera anymore. And cholera is still a problem in the world due to poor sanitation. In Brazil, it has been probably completely eliminated, I think, due to just urbanization and better sanitation. Even you have many places where have bad sanitation in Brazil, but still it's already enough in order to avoid an epidemic of cholera. Okay? So, and the same, I mean, the same. Tuberculosis the bacterium was discovered by Koch, and that was easier to. I mean, this is transmitted by the air, and still there was a problem. I cannot avoid people. I can do sanitation for cholera, and I can also avoid contact with rats and fleas for plague. So that was the hygienist view of the things, which for the diseases has worked well. Tuberculosis was more difficult. You cannot avoid contact. So we had to wait much longer in order to have not only the transmission route, but how can we save the lives of people the sick people by healing them. Okay? So this you have to wait for almost the middle of the 20th century with antibiotics. Then you have something. Okay, so there are many intrinsic things, and but this knowledge, for instance, related to cholera and to plague, has generated a lot of a kind of view that society has to be clean. So this is what's called the hygienist view, which has had very complicated consequences when taken out of the context of infectious disease transmission. For infectious disease, it's true that you have a clean house, you don't have the rats, you don't have the fleas, you don't have the contaminated water, and therefore you don't have the diseases. But people obviously took the idea of hygiene out of the context of disease transmission to the cleaning of the society. And this obviously took a very bad turn with eugenics and this kind of thing. But it was inspired by the success of the theory of microbes as the transmission of diseases. Just a comment about infectious diseases. With the discovery of the transmission routes and with antibiotics and with a series of discoveries about how to treat people, at a certain point, in the context of the World Health Organization and so on, like back to 1970 around, infectious diseases started to be seen as a minor problem. Well, obviously this was thought about minor problem in rich countries. Right? They've always been a problem in poorer countries, but as a minor problem. Right? And that's what that changed when we have the notion, which is a new notion, that is the new emerging diseases, which most clearest case was HIV/AIDS. It's a new disease. It's a virus. It's transmitted. It's infectious disease. Very different. And then you have all the new diseases that appear. The influenza, different influenza things, and so on and so on. So this created this idea, which is typical from the end of the 20th century, that there are diseases that will emerge. That was not really something that people thought much about before 1970, 80 or something. So, but still, if you look worldwide, there are the main causes of disease. There are still infectious diseases that have importance as cause of disease of death. It depends essentially on the region of the world they are looking for. So maybe, okay, now it's time for you to give me a suggestion. What are the main infectious diseases important in today? Diseases that are important as a cause of death. infectious. The main cause of death, for instance, in Western society is cardiorespiratory problems, this kind of thing. But is there anything infectious that is important? Hmm? Yeah, well, COVID. Yeah, COVID. It's a new emerging disease. But, dengue, no. Dengue is a very very important public health problem. But so how many people do you think that will die of dengue in a year? Yeah, in Brazil.
There was a disease, I forgot which one it was. We already have vaccine for it, and it started emerging again, like for the past 2 years. I just forgot the name of it.
Measles.
Yeah.
Yeah, measles. So, okay, let's dengue. It's about the average before the years of COVID was like 800 persons per year, okay? Which, I mean, it's the point of view of being a major cause of death. It's not. Okay? You mentioned measles. Measles is also not so important as a cause of death, okay? Because measles is an but we will then discuss in the mathematical part something which is connected to why did measles reappear. Right? But other one, which is very, very important, and if you look on the data worldwide, is malaria. Malaria is a very important cause of death in Africa, and very important. And not in Brazil. Why? Well, but first, it's typically connected to some rural areas, and you have strong urbanization in all the coast and in the south of Brazil, southeastern, and so on. So that you don't have malaria so much. Malaria is typical in the Brazilian case of border of forests, border of Amazonian forests, and semi-rural settlements. You know, many of them are this kind of illegal invasions and so on. Then you have, because in the forest there is no malaria. In pristine forest, why? There are no people there to close the cycle of the disease. So if you don't have any people, and the malaria is specific to humans, then you don't have malaria. So you have to have the people, but you have also to have an environment where the mosquito can survive with certain temperatures and so on and so on. And this is what you still have at the southern border of in all Amazon region. Okay, and one thing is that there's not so many deaths of malaria in Brazil. It's that kind of malaria is the etiological agent is a protozoa, okay, which is how it's called, Plasmodium. And there are many kinds of Plasmodium. And there are two main Plasmodium types that circulate in the world, which is Plasmodium falciparum and Plasmodium vivax. In Brazil, we have predominance of vivax, which is milder. It is a the disease is not so effective in people. It's not so severe. Although Vivax has a dormant state, and it stays in your liver, and you can get back without having contact with anything. You can get sick again. Yeah. But still, most of the time, people survive, which is not the case for falciparum, which is a very important cause of death in rural settlements in Africa. Right? We know how it is transmitted. It's this mosquito Anopheles, and There are many kinds of Anopheles also, but essentially it's mosquito-borne, and that's it. Yes. So, okay, this is and another sometimes another cause of death, which is emerging as we don't know what will happen. I mean, due to infectious diseases, is why it's not working? Is tuberculosis. There's a re-emergence of tuberculosis. Oh, come on, stalled. Why are you stalled? It seems it's okay. And still an important cause of death, tuberculosis, due to resistant tuberculosis. And I forgot to mention. I forgot also to mention that one of the very important epidemics in the 20th century is what is called the influenza pandemic, which is called Spanish flu. Actually has nothing to do with Spain. It was an historical error, but well, got this name. Okay? And this was very, very frightening. It is 50 million estimated human beings died of it. 1/3 of the world population was infected. And it's like COVID, it's transmitted directly. And here are some curiosities that we will take into account in our models. So in Sao Paulo, for instance, first death occurred on October 21 October 1918. But at the end of November, there were no infections anymore. Nobody had a way to avoid, I mean, people could stay at home and so on, but there were no treatment. People just went to the hospital and people saw what can we do. Right? And, but it went away, and if you look worldwide, 1/3 of the world population in all continents except Antarctica, this really was a real big pandemic, a super pandemic. But it's not everybody that was infected. Okay? It's on 1/3 of the populations. And without having real ways of opposing the pandemic, it went away alone. Okay? So it kind of, indeed it was locally very fast. It is something that arrives, has a super peak, and it goes away like 2 months. 1 month, 2 months. Okay? So it's a fast thing. So this is things that we should remember when you go to the models, because with the models, we want to also, with the first models, which are kind of simple models, we want to understand why this kind of thing happens. So most diseases don't, even after having an epidemic, most diseases don't affect all the population. Okay? And some of them may affect, but others not. So why? Right? Where is the difference? Can our models explain this kind of thing and understand a little bit what is happening? Right? So, okay. Any questions or comments right now? We'll start the mathematics. Yeah, where's the mic? Mic. Okay.
Is that number of 1/3 of global population infected by the Spanish flu Is that a number that we can fully trust? To
Well,
rely upon it to build
well,
a
this
model?
is estimations. Yes, it's estimation. It's not counting. It's not that this was counted. Okay, so I don't know exactly how these estimations were done, but 1/3 of got infected, not died. Huh? And I don't know how people actually estimated this, but this is it's populational estimates. Okay? That's like things that people do with COVID also. So to know the number of people that got in hospital, there's a proportion that you expect of the number of people that got infected, get onto the hospital, and you have the hospital records, and so you more or less estimate the total number like this. Okay, if it's 1/3 or 1/4 or 1/5, I mean it's a large proportion of the population that has been affected.
And then it like, because I was thinking it would be possible for a person to have contact with a virus and not get infected at all.
Yeah.
But could you explain like why does that happen specifically? Apart from like maybe it's there's not enough virus for the person to be contaminated, or her system acted fast, or is that something to do with like genetics?
So this has to be with two things, which is usually there's what people call the transmissibility and the susceptibility of the persons. So so all of those diseases usually they have so first one is the person getting infected, and the other is generating an epidemic. This is different things. So person can be there are many reasons. So you can have contact with the virus, but maybe the virus needs a certain humidity or certain temperature or whatever, and maybe this is affecting the transmission. So transmission is not sufficiently effective usually. So the number of people that get the diseases, percentage of the people that get the diseases with respect to the number of people that had contact with the virus is usually very small, like 5%. And then there's also the individual susceptibility of people. It depends on your immune system, depends on the kind of virus. It's a virus that is new or not. For instance, COVID is new. Nobody had immunity. But then you have the kinds of dengue, for instance, where you may have immunity, but you may have partial immunity. So there's a likelihood that you will get infected or not. And they will get, in once infected, that you get the disease, because it's also different. Okay? And then for the epidemic thing is, okay, there is a virus, and I'm here, and usually if it's like respiratory things like COVID or many others also, one thing that promotes the epidemics is if you have a phase, or if you have people that are asymptomatic but may transmit, which is a problem, big problem. Others also, like COVID, many cases, you have you are infectious, but the disease takes some days to develop, and then these days before you transmit. Okay? So most epidemics, for instance, like if you take COVID in Brazil, that is, you say the first case was in the state of São Paulo, 28th of February 2020. Not necessarily. This is the case that originated the epidemic, because there are multiple introductions. So this is what maybe just by chance the case that was detected early and so confirmed. Not necessarily. These are the cases that started the transmission in the population. So in the case of COVID, it's in multiple introductions, and then once you get a situation where you have a lot of transmission, then usually it has to do with some super spreading initial. initial spread has a lot of relation to super spreaders. For instance, there was a famous case of a party where in March, or I don't remember, 2020, a party in Trancoso in Bahia, where a guy knew he was infected, went to the party, and then there are lots of people that got it. Okay. So, yeah. Okay. So, in order to start the building blocks for mathematical models, so we will approach as simple as possible, and obviously there's a lot of ways to improving this, but we'll start that the population is what we'll call well mixed. Well mixed is that everybody can have in principle contact with others. Does not mean you have contact with everybody. In principle you can have. And in a human society usually you have a certain number of contacts per day, but could be anybody in principle. So it's not obviously true due to the spatial extent and to the structures of human society. And but we will take this. This was also actually assumed when we did the ecological models. Okay, so and we will also discuss. We take no space as we did within ecology. Space is homogeneous for us. Okay, you don't want now to discuss the effects of spatial heterogeneities. What is spatial heterogeneity? For instance, if you take cholera, it's where you have sanitation and not sanitation. Okay? So then you have to take into account this. But we will not at the first step. We do not. So we will classify all individuals in 3 compartments. The susceptibles, which are people that can have the disease. The people that are infected or infectious, that's used interchangeably, but should be taken care. What is important is that the person is infectious. It can transmit, for the point of view of a model. You can do better models, but people that are incubating and so on, you introduce new classes. But here, the most simple one is just one class, which is the case of infectious people, and the infectious people that get recovered, and which we will include through immunity, or you could say, okay, from the point of view, it could be also dead because a person will not transmit anymore. Okay, so, but so that's kind of structured population. So, next step. So we are not interested in the demographic dynamics of the population. So we want to study the epidemics in a given population, for the conditions for occurrence, prevalence, and so on. And what we will do is consider that the human population has a constant size. The population which has been studied, right, which is also sometimes very, very complicated, for instance, to know what's the relevant population, because you should use the population at risk. For instance, there have been, with Zika virus, there have been studies, and for instance, I've seen that in Colombia, trying to estimate parameters using total Colombian population, which was completely wrong because it was only connected to a certain region. So you have to use the population at risk. Okay? But then we will consider population constant, because the demographical changes occur on long time scales. You know, in order to have, say, the doubling of the population, it will take centuries, or even an increase of 1 or 2% takes years and years. And the dynamics of the epidemic are usually fast. Okay? Months. There are cases of endemic cases, which is something which are popular, is when we have a disease that you may have an initial epidemic, but then it settles to a certain level of infected people, which are usually slow in the society, small in the society, and stays there. So this is an endemic. Like today, HIV/AIDS is endemic. It's not epidemic. And okay, but we will assume constant population. Once we have this, we will and we will talk about directly transmitted diseases. When you have diseases which are vector-borne, there is some either an animal or water or whatever that is the route of transmission, you can have different models, but sometimes these models are also okay, in the sense that if I have, say, I got malaria and something. Oh. Okay. I got malaria, and there's the mosquito, and the mosquito transmits to one of you. It's like the contact mediated, and some models you can use this as a contact which is like direct. Okay? And this is sometimes a simplifying assumption because human population is something that's very well studied. For instance, we know the size of populations. Okay? Mosquito populations, for instance, are not well studied. How many mosquitoes do you have? No. Difficult at all. So the first thing is we will assume that per capita change of susceptibles is proportional to the number of infected, which means that per capita it would be 1 over S ds dt, and we are assuming that this is just proportional to the number of infected. Okay? So that's one point. And here comes an important discussion, which has been, which is a source of many errors in many modeling attempts. People, usually more people from mathematics or physics, try to do some real world theory about diseases and epidemiology. Many forget about something. This R, which would be the force of infection. The force of infection is R times I. And R is the proportion constant. Now, let us write it again with the multiplied by S. Now, we should take R as depending on the size of the population. So we will write this as beta over n. Why? So if you write this in this way, then you have ds dt is equal to beta over n I times S. And now, if I divide this sides, both sides, by n, okay, I will use lowercase for S over n, which is the proportion, the fraction of susceptibles in the society, in the population of size n, and I will use a small I here for proportion of infected persons. And then if I divide both sides by n, I will have d dt. You will have S over n, which is the small s, which is just a fraction. Here you will have beta. You have I over n here already, which is I. And you divide it by n on both sides, you get this. So this is an equation which is only for the fraction of persons. It does not depend on n. This is consistent with the fact that, oh, yeah.
I think there is a minus sign there.
There's a minus sign. Yeah. Okay. Yeah.
Small s.
This is small. Yeah, this is my small s. Yeah. And so, what does it mean? Is it very different to have an epidemic, say, in São Paulo and in Campinas? Not so much. The total numbers of people infected or diseases or whatever, they depend on the size of population. But the characteristic, the fact that you have a certain increase rate, then a certain duration time of the epidemic and so on, have been observed in many places in the world. For instance, with Spanish flu, that it takes more or less 1 or 2 months to go from arrival to the end. And this is independent of if you are talking about a city like São Paulo or a small city or a super big city. Okay? So the epidemic model for humans should not depend, the essential characteristics of the epidemic do not depend on the size of the population. Okay? That's important. Why? Why is it so? So, speculations. Why are the characteristics of epidemics? For instance, take the typical time from arrival to the end of the epidemic. Why does it not depend on the size of the populations? Yeah, Mike. Yep. This one is the good one.
So I didn't understand how you divided the first equation by n, both sides, and the n disappeared. Because
I divide by n.
If you divide beta over n by n, why n disappears?
So I divide by 1 over n and 1 over n. Okay? Yes?
Yes.
So the s over n is the small s.
Okay.
The beta is here. Then you have 1n, 2n. So I can just write this as the same as beta I over n s over n. Therefore, this is small, lowercase, which is right here. That's why I have the 1 over n. Here I have a product. Okay? Not clear? So I will do it again. ds dt is equal to minus r s times e. And then I will say r is equal to beta divided by n. But I will write it already here. Okay? Okay? I can divide by, I have the equation. Okay, and I divide, now I take the equation and I divide in the right hand, left hand by n. Okay? So 1 over n here. And I multiply this by 1 over n here. So I will write it here. Okay? So you will have d small s dt, because this is the same as d dt of, because n is constant, of s over n. Okay? Therefore, you have ds dt here is equal to minus beta. This is the lowercase n, and this is the lowercase I. Still not okay? So this equation, which describes the fractional susceptibles and the fraction of infected people, does not depend on the size of the population. So, okay, or still? So the idea now is, okay, when I will derive several things about from this kind of equations, okay? And usually we will use it in this form here, okay, with ds, the big ones. But now, why is it that the population, for instance, the total time for the epidemic or the initial increase of the epidemic does not depend on the population size? Now, speculations about this.
because even though the time it takes to infect everyone is proportional to n, the infection rate is also proportional to n.
Yeah, and why? I mean, the infection, depending on what you call the infection rate. But, so let us think about how is the infection. This depends on what? On contacts, yes? Are contacts very different from here in, say, Campinas? You are here, we have 10 times the population of Campinas. And so it's more or less what you said, but the idea is that the structure of contacts is something which is connected to the society, of the human society, and the number of people that you meet, and you have potentially contacts that could transmit the disease, it does not depend on the size of the city. Okay? There could be minor effects like public transportation could be increase the number, and but usually these effects are actually small. So this introduction of this r equal to beta over n, so we have the dependence on n in the equation, is connected to the structure of human society. It is not necessarily true for animals. Okay? So mainly when you have diseases in, for instance, in cattle or animals that humans can manage and can make the for animals that don't have a structure of society, then if you just have a higher density, higher number, they have proportionally more contacts. And that's, for instance, the origin of many of the problems we have, for instance, with fish, like salmon. Okay? It's created in a cage. So these salmons are all the time full contact, very different from if they were just fish. And that's why the use of antibiotics or whatever thing they put in order to avoid, because it's for something like this does not happen with the human society. So, okay, so let's go for the equations. So we have already written here, this is the first one, okay? I'm using still the r, but remember, r is beta over n, okay? And then I will say the following. Everybody that got infected, who were susceptible, goes into the compartment of the infected. Efficiency 1. So this is like Lotka Volterra, because you have a minus sign here. So S is playing the role of the victim, of the prey, and I is playing the role, analogous obviously, as a predator, but the relation here is not like before, where we had always an efficiency. Now, one person that gets infected and one susceptible that leaves the susceptible compartment enters the infected compartment, and this is efficiency 1. Therefore, it's the same constant. And then you have here something which reminds of our mortality rates, but it's not mortality. It's like the infectious leave the compartment in a linear way. So it's like mortality, but it's not the person dying, it's the person not being any more infected. So it's like mortality of the infections, okay? So, and then we will assume that all people that got infected leave the compartment of infected and go to a compartment of recovered, also with efficiency 1, okay? So, and here we will assume for reasons of simplicity, but something that can be obviously modified, that people remain and got immunity, and there is no waning of the immunity. There's not people getting infected again. Okay, so that's a simple. That's what works well with like measles or chickenpox and so on. You do get actual immunity for the life. For instance, it does not apply to malaria. So, we have these equations, and now we want to look at what these equations tell us. Yeah. We will not proceed. And first, we don't have the analytical solutions. Again, it's like our other models, no analytical solutions. So, we will do some analysis of quantitative analysis, but we will first, okay, first we will pose a problem that we want to solve. It's not just obtaining equations, the solutions. And first thing is, observe that if you add the first, the second, and the third equations, then you will get that s plus I plus r d dt has a zero derivative, and the total population is constant, and we will call it n. Okay? So the total population is constant, and your system of equations is compatible with what we have assumed before. We will now pose the following question. Say at time t, you have a certain number of people that are susceptible, and you introduce a certain number of infected people, and you have nobody immune. That is the case when you have a population which has not been exposed to a certain etiological pathogen, and you have the introduction of the pathogen at time 0. And so the population is composed at time 0 only of susceptibles and infected. Usually we will take the infected much smaller than the susceptibles, okay? The calculation is for S0 and I0 arbitrary, but will be relevant when I0 is close to 0. So only some small number of initially infected people. So given the equations, this equation has two parameters, R and A, and given the initial conditions, we want to know if there will be an epidemic. And mathematical definition for us of an epidemic is, will the population of infected increase over time, initially? Okay? So we want to know if the time derivative of the number of infected at time 0 is positive. If it's positive, means that you will have an increase of number of infected. Doesn't mean that it will increase forever, okay? But initially it will increase. So we want to know when this happens. So notice that at time 0, you have, by the second equation here, I have it above. Here, this equation. Okay? At time 0, I calculate this at time 0, I will have R S0 I0 minus A I0, which is proportional I0 R S0 minus A. Okay? So, all will depend, let me put this in. All will depend on this, so d of I at time 0, it will be proportional to I0, which is a positive number, times R times S0 minus A. So it's a sign of this that will determine if the derivative is positive or negative. Okay? So if the population, if you have this first case, if S0 is smaller than A over R, then this is negative and there has been no introduction, no progress of the epidemic. You introduce a certain number of individuals with an infection, but the number decays. Once it decays, it will disappear. This is not an epidemic. On the other hand, if this is positive, then you have an epidemic. Okay? So, okay, let's skip this. There's some mathematical thing, but let's stay with the result that if S0 it's bigger than A over R, there will be an epidemic. So, and again, pay attention. Initial increase of the number of infected is the definition of our epidemic. Does not mean it will increase forever, because the time derivative for I will change over time. So, then we come to this conclusion that what we had was S0 has to be bigger than A over R, which can be written as S0 times R over A has to be bigger than 1. And this is what we call basic reproductive number of an epidemic. Okay. So, sometimes basic reproductive, I wrote ratio here, but can be also ratio, but more commonly a number. Okay, so this is derived in this context as the condition that arrives mathematically for the increase of the number of infected in a population. That can be also thought about that is the condition for invisibility of the human population by a pathogen. Or also mathematically, you have, it means that the disease-free equilibrium, which is everybody is just susceptible, is unstable. Small introduction of a certain number of individuals will trigger an epidemic. Okay? So, this number, we want now to discuss a lot of this number. So, let's do it on the blackboard. We still have time. Yeah, we have some time. So, where's the... So first, some simplifications. Okay, so we defined R0 in this context equal to S0 R over A. So this has to be bigger than 1. And whoops. Did I write this correctly? No, probably not. Let me go back here. Did I mess up something? Where's my pointer? Left pointer somewhere. I always, here. Maybe I messed up something here. Oh no, it's not correct. Okay. Yeah, correct. Everything. It doesn't matter after anything. Okay. So we have this, and the condition is R0 bigger than 1 in order to have an epidemic often. You can rewrite this as the following. Remember that R is some beta, which is independent on the number on the size of population divided by n. So I plug into this, so then you will have S0 and over n will be times beta times divided by A. Okay? So this is the proportion of susceptibles at the initial time, and we will take it very close to 1. So we have a population which has a certain number, a population which has not had contact and has no immunity Therefore, this population is very close to total population. So this is will be taken by us now as beta over A, and this is the simple simple expression for the basic reproductive number. So, what can we do with this result? Okay. So the first thing is we better try to have our population we don't want the epidemic to enter. Okay? So suppose you have the arrival of a pathogen through introduction of an infected person. We want R0 to be smaller than 1. That's our objective usually. R0 smaller than 1, the population has what people call herd immunity. Okay? So what are the ways I could, what does this say about getting R0 smaller than 1? Now, first, one way is to find out ways of manipulating beta and A. So beta in the equations was this kind of thing. Right? That was the equation. So beta is related to the contagion. So if beta is big, then you have a very, very sharp diminishment of an increase of infected. Okay? So beta is connected to what? We have the encounter. We need, like in predator-prey models, the encounter of, in this case, a susceptible and infected, and beta will be proportional to the probability that this encounter actually is effective. Okay? So if beta is very small, for instance, then you would say, even if you have a high number of infected people, the number of people from the susceptible population will decrease very slowly because beta is slow. Why? Beta is small. It's small because the efficiency of the transmission is not very good. So beta has to do with the transmission process. One way of looking at this is say, how can I lower the number of infectious contacts? Right? So if I have a lower number of infectious contacts, I am lowering the value of beta. And if I lower beta, I get a smaller value of R0, and I could think that maybe we could, by restricting the contacts, make R0 be smaller than 1. How do we restrict infectious contacts? Ideas?
Staying home.
So one thing is put everybody at home. Okay. In other ways, masks also. Okay, so masks and other ways. Other way is if the person gets sick, has to be isolated. Therefore, the number of infectious contacts diminishes. Okay? So in this small formula, we already see that this R0 can guide us on what matters to obtain a situation where the pathogen cannot invade. Okay? Now, And then there's this A. We want A to be big. But A appeared in this equation. So this is something which has to do with what? With, if you don't look at this, this is connected to the duration of the disease. If the duration of the disease is short, then people will live much more faster, the class of infected people, and go to the recovered. Okay? So if A is big, then okay, sorry. So A has the dimensions of 1 over time, and 1 over A is the typical duration of the infection. Right? So if you want to have a big A, in order to have R0 smaller than 1, we want to have a big A means that this duration of infection, which is 1 over A, will be small. So how can we have the duration of the infection smaller? How?
Treatment in general. Treatment in general.
Treatment, yeah. So treatment at early, here we are talking about a population that's susceptible, and there are few infected individuals, and if we want to avoid the existence of epidemic, means that early treatment would be very important. This is obviously very difficult for emergent things, okay, like COVID, because you don't have the treatment. Okay? You can only manipulate like beta, okay? So beta is more easy in this case. But for other things, where you have treatment, okay, early treatment can avoid the invasion. The mic, where is it gone? The mic. Here.
Does this change for diseases with high mortality like rabies, which has 100% mortality?
Yeah. Yeah, then you have to change these equations, obviously. Then you have to put a mortality rate, okay? A real mortality. So, in fact, real mortality, well, it depends on the prevalence. If the prevalence is very small, you can have the mortality, but you still have the population constant, approximately constant, okay? You have 1 million people, and you have a high mortality. The prevalence is very low, then you have, say, 50 people dying. We have 1 million. That's still good approximation. The population is constant, but you have mortality. This mortality term, which is called technically as the virulence of the disease. Okay? So there are very interesting theories and discussions about what's called the evolution of virulence. And this is connected to the fact that they have some of the more virulent diseases, some of them do not spread well. Ebola, when Ebola appeared first, there was kind of panic. This has some very high mortality rates. So virulence is very high for Ebola. But I mean, it gets restricted in a certain region. Okay? So there's a kind of trade-off probably. So the origin of the trade-off can be discussed lengthily. In some sense, people dying very fast. Because, I mean, Ebola would be like people getting an infection of Ebola immediately triggers isolation or death. And therefore, the number of contacts is restricted by self-restricted. And which is exactly the contrary of mild infections, like say measles. Measles, I mean, I don't want to say that measles is not important, okay? Because the people die of measles, elderly and also some young. But anyhow, the virulence of measles is relatively small, and it has a very high R0, okay? So before we go for the coffee break, let us explore a little bit what are the values of R0 which are around, okay? So I have this, I found a place, I don't know, Wikipedia or whatever, where we have this, this is somewhere here. So this is the typical thing that you find, for instance, that has been produced by American Center of Disease Control and by World Health Organization. It's clearly centered on certain diseases, which are not, except for cholera, they are not the tropical diseases. You cannot read this, yes? It's too small? Oh, okay. So, okay, let me. Better? Okay. So, for instance, this has already the coronavirus, which the wild strain, okay? Not the variants. Variants are multiple. So it's kind of three, okay? And which is more or less connected what the Spanish flu was. Okay, so it is not so big actually, the Spanish flu, but it has a high mortality. That's and here you see these are typical values, but you know this typically diseases of children. For instance, measles is like more or less 17, right? And pertussis, pertussis, which is in Portuguese, which is coqueluche in Portuguese, is also like measles. Okay? So then you could ask yourself, okay, what does it mean to have a high or not? So, well, the first thing it means that if a high R0 will have an initially very fast increase of the infection. Okay, so now for the next part, we want to have a better idea of the meaning of R0 and how it is related to a more common definition of R0, which is the number of secondary infections created by each infectee, and how this thing is connected to that notion, which is the more epidemiological way of thinking about R0, and gives an interpretation of this formula. Okay, and then, if we have time, we can also discuss other ways of diminishing R0, which would be to have the initial population, not all of them susceptible, because here we are in the approximation of whole population initially susceptible. One way of having a smaller susceptible population is vaccination. Therefore, you can, from this, we will be able to derive a condition of what's the proportion of vaccination of immune people that has to be vaccinated, of the susceptible that have to be vaccinated in order to have R0 smaller than 1. And this is connected to the measles, new measles epidemics we had, for instance, in the Amazonian region some years ago. So okay, let's stop for the coffee break now.